Hello everyone. In this video, we are going to look at forced vibrations of multi-DOF systems. And by force here, we are only focusing on basically harmonic forces, although we can generalize it to any other force later on, but we just want to focus on harmonic forces. And to demo that, we're going to look at the 2-DOF mass spring system again here. And we assume that the forces on these two objects are F1 sine omega t and F2 sine omega t. So first, we assume that there is no damping, and we assume that the frequency of the forces on these two objects are the same. That's the simplest scenario. Later, we can add damping, and we can make those frequencies to be omega 1 and omega 2 to make it more general. And we're going to go through all of that in this lecture. So first, if we deal with the simplest case, which you can see in our reference book, in the reference book, only this scenario is handled. The other more advanced scenario are not. So here I'm adding some extra information. So clearly, the equation of motion is going to be m1 x1 double dot equals sum of the forces in the x direction. So it is going to be that f1 sine omega t minus k1 times x1, and then minus k2 times x1 minus x2. Here we assume that x1 is bigger than x2. And then you can bring all of the x1 and x2 to this side, and that is going to give you this one. And similarly for m2 also, we're going to get something similar. So it's going to be m2 x2 double dot equals f2 sine omega t. And then the reaction of that force, so that is going to be plus k2 times x1 minus x2, and then minus k3 times x2. And again, bring all of the x1, x2s to this side, and you're going to get this one. So these are my two governing ODEs, and if I write them in terms of matrices, I can write it as mx double dot plus kx equals f, where vector f is this one. This is matrix M, this is matrix K, and this is matrix X, vector X double dot, and this is vector X. So I can write the system in matrix format. In the previous video, you saw this right-hand side was 0, so that was free vibrations. Now it is this arbitrary vector F with two magnitudes F1 and F2, but both share the same frequency again. Okay, and as I said, we can make them separate frequencies later. But this is my forcing function on the right-hand side, and it could even be any arbitrary function. So, first, what kind of solution can we assume for this system? This system has no damping, therefore the solution can be simply considered as two magnitudes, x1 and x2, with the same frequency and no extra phase. So they're going to be x1 and x2 times sine omega t for x1 and x2. And you might say, why don't you have, and by the way, this solution, when I say this solution, here we are talking about steady state solution, or so I added it for you, or a particular solution. So the solution that I'm looking for is x1p and x2p, okay? The homogeneous solution can come from the forming the characteristic equations, and the thing is with that homogeneous solution, that if the system is stable, which it is in this case, that term very fast typically goes to 0. So here I'm looking into steady state solution, okay? That is very important, and we just neglect the initial transient response, that there are some small oscillations in the system. We just look at the steady state solution. Now, let me show you one more time why, when there is no damping, we don't need an extra phase. So if I go back to my previous videos, where we had 1-DOF system, and we had those responses. So right here, look, if you look at the magnitude and the phase formulas, look, you see that the phase formula needs to have a zeta, and zeta, if you remember, it is c over 2 square root km. When there is no damping, they are 0, and when it's 0, tangent inverse of 0 will be 0. So an extra phase is needed in the solution if and only if there is damping in the system. In this first scenario, there is no damping, therefore I do not need to assume an extra phase in the steady state solution or in the particular solution. Okay, so if I go back here, I do not need to consider a damping. All I need are these two unknown magnitudes that I need to find. How do I find it? I just plug these two solutions into my governing equation. So here, wherever I have x1 and x2, I plug it in, and then I need to take two time derivatives from them, correct? So which give me negative omega squared x1 sine omega t, negative omega squared x2 sine omega t. So if I plug them in and replace, I will get this equation here if I merge all of them together. And if you look here, this matrix here, which is like k minus m omega squared, basically, this matrix is basically all known parameters because omega is a known value, k and m's are all known. F1 and F2 are also known. The only thing unknown is this matrix, so all I need is to inverse this k minus m omega inverse, multiplied by the magnitudes f, and I get magnitude x, and that's it. Once I find them, because these are just numbers, once I find magnitude x1 and x2, I plug them back here, and guess what? That's my particular solution. Again, for homogeneous solution, you have to set this side to 0. You have to go ahead and find the eigenvalues of M inverse K matrix. Remember, like we did last time when I talked about free vibrations. Remember, in free vibrations, all you have is homogeneous solution. There is no particular solution. And we found that in the case of no damping, we just needed to find the eigenvalues of this matrix, and the homogeneous solution will be exponential of that. So if it's just negative numbers, then you will have decaying exponential. If they are negative plus some imaginary part, then they will be decaying harmonics. And so we can get those as well. Okay, so we can get the homogeneous part from last video. Please take a look at it. Free vibrations of multi-DOF systems, and get the particular solution here and add them together. Okay, so if you want the total solution. Now, in scenario 2, we make basically the two frequencies to be different. So each one of these harmonics has its own frequency. Still no damping. So now my forcing function is going to be this. And the equation of motion is still the same, the left-hand side, of course. Now this time, because you have two harmonics, you have to consider both of these harmonics in your solution. So x1 particular and x2 particular, the steady state solutions, are going to be two unknown magnitudes times these two basically frequencies, and similar thing goes for xp2. So here you have four unknown magnitudes to find, but again, because there is no damping, none of these harmonics needs a separate phase. All they have is these unknown magnitudes. Now, if I go ahead and plug in these solutions into the original ODEs and sort it out, so this is if I plug them in. So plug them into the original ODEs, you get this. Now here, if you look, on each side, we have a bunch of sine omega 1 t's and sine omega 2 t's for both of the equations. For instance, if you look at omega 1 t, what are the coefficients of omega 1 t on the left side? It is m1 negative x11 omega 1 squared. Then we have basically this term here, which is k1 plus k2 times x1. Then we have negative k2x21 sine omega 1t, and that's it. On the right-hand side, the coefficient is simply f1. So if we set these coefficients equal, this is your first equation that you will get. On the other hand, your cosine components are, sine of omega 2 components are these. Look, this is 1. This is 1, and this is 1. On the right-hand side, there is 0 sine omega 2t. So these three terms, their coefficients, when you add them together, sum of it should be equal to 0, and that gives you the second equation. And then you go to equation number 2, again similar, look at the sine component. So here is one, here is one, or sorry, here is one, here is one, and again on this side there is no F1, so that should be equal to 0. And finally we get this term for omega 2t, this term for omega 2t, this term, and F2. So some of those coefficients should be equal to F2, and this is that one here. There we go. You see? So I got 4 equations, and you can write these 4 equations in matrix format like this. So the first 2, if you look at them, the only unknowns in the first 2 are x11 and x21. So you can write it as a 2x2 set of equations. The next 2 are x22 and 12. So again, you can write it as a 2x2, and from here, by inverting this one, multiplying by this, you can get this portion, and then by inverting this one, multiplying by right-hand side, you can get this portion. There we go. So you got all 4 of your unknowns, and that's it. You got your solution. Okay, because once you have the 4 magnitudes, you plug them in, your particular solutions are known, and again, homogeneous solutions, you find it from my previous video on free vibrations of the systems. So you see, it doesn't matter if these frequencies are not the same. All you need is to add more terms, because for each frequency, there should be a component in the solution. Good. So now this is when frequencies are different. Okay, now we would look at the hardest scenario possible, which is when you have damping, and here 3 dampers, 3 springs, and 2 forces with different magnitudes and frequencies. The most general case you can have, harmonic excitation of 2DOF system. And the question is, can we get any possible analytic solution here? This case is completely, as I said, not covered in the textbook and in many other textbooks because this is too hard. So the answer is yes. Now, since you have damping, you should have a phase added to the response harmonics. And so if you look at your particular solutions for X1 and X2, then they will have each one, both of the harmonics with some phase added and with some magnitude. And these magnitudes and phases are different for X1 and X2, so you will have 8 unknowns here. Now, if you plug these 2 into the governing equations, which are provided here in this let's see if I have it here in these equations, correct? Except that these guys are going to be F1 and F2, right? Times sine omega t and sine omega 1t and sine omega 2t. Okay, so if you plug that into the governing equations, then you will get these 2 ODEs. This is the first ODE for mass M1, and this is the second ODE for mass M2. Clearly, you see how big they are, because there are all sorts of terms here, the K's, the C's, the MX double dots, and so the governing ODEs are big. Now, here you have to use some trigonometry formula. Here you have sine of something plus angle and cosine of something plus angle. So here you have to use these formulas, that sine of, in this case, let's say if I use omega 1t, let's say, and then plus phi, okay, or let's just use omega for general. This is basically sine of omega t times cosine of phi plus cosine of omega t times sine of phi. And then for the cosine one, cosine of omega t plus phi is going to be cosine omega t cosine phi minus sine omega t sine phi. And then when you expand these trigonometry terms and set the 2 sides equal, you have to pay attention that you will get a bunch of terms on the left side that are multiplied by sine of omega 1t. So sine of omega 1t will be multiplied by a bunch of things, and then cosine of omega 1t will be multiplied by a bunch of things, and then sine of omega 2t will be multiplied by a bunch of terms. And finally, cosine of omega 2t will be multiplied by a bunch of terms. That is equal to simply f1 sine omega 1t. Okay, and then of course 0 times cosine omega 1t plus 0 times sine omega 2t plus 0 cosine omega 2t. And when you do that, now this coefficient of sine omega 1t will be f1. The coefficient of cosine omega 1t will be 0. The coefficient of sine omega 2t will also be 0. And finally, the coefficient of cosine omega 2t will also be 0. You see that? So you are, seems like, I picked the wrong tool. Let me use another one. Maybe this bigger one can do. Okay, so now that will give you 4 equations. And these are those 4 equations. Look, these are those 4 equations from the first one. By setting the coefficients of sine and cosine omega 1t and sine cosine omega 2t on both sides equal, you get 4 equations. And you repeat the same thing for the second one. Now in the second one, the sine omega 2t has coefficient f2. Omega 1t has nothing on the right side, both sine and cosine of it, and omega 2t cosine of it is 0. So if you look at the second one and set those equal, you get another 4 equations. There we go. So you get 8 equations and 8 unknowns. But guess what? These equations are no easy to solve. Even if f1 and f2 are given and all the k's, m's, c's are given, finding the cap x's and these phi's, these are 8 what we call transcendental equations involving sine and cosine. So analytic solution of that is not trivial. They are not linear, and it's not trivial. I think it's probably impossible. So the best way to do it is to use a numerical solver. So you solve these 8 nonlinear equations with a numerical solver like Newton-Raphson, and you find values for these parameters. Once you have those parameters and plug them into these 8 places, now you have your full analytic solution for particular xp1 and xp2, and homogeneous is like the previous video. So pay attention that although we need to solve these constants numerically, it doesn't mean our functions are numerical. Our functions are analytic. But in order to find these coefficients in them, we might need to solve these 8 equations and 8 unknowns numerically. Okay? Unless there are a lot of them that are 0, a bunch of these m's or k's or c's are 0, and then, yes, maybe you can do that. But in general, that's not a trivial problem, as you can see. Okay, so but there is a solution in general. And here, to show you a demo in MATLAB, here I made the same system. So this is M1 and M2, and I use SimEscape blocks, SimEscape mechanical translational blocks. And you see these masses, you can provide their values. So this one is 1 kilogram, and the initial velocity of it is 0. This other one has mass of 2 kilogram, again initial velocity of 0. Then we have these springs, so their initial deformation are 0. This one is 100, this one is 200, and this one is 150. I also have dampers, and this one is 20, this one is 40, and this one is 30. Okay, so I have C1, C2, C3, K1, K2, K3, M1, and M2. I provided both of these masses with different harmonics. So the input to this one is 10 sine of 25t, and for this one is 15 sine of 45t. So you see omega 1 and 2, F1 and F2 are different. And I passed them through these ideal force sensors to these objects. And then with the ideal translation motion sensor, I am measuring their position only, and I assume that their initial position is 0. If they are not 0, you can provide a different number here. So you see the initial positions go to the sensors, the initial velocities goes to the masses. Okay, and you can not only measure their positions, you can measure their velocities or accelerations if you want to see them in the oscilloscope. But right now I only care about their position, so I just check this one. And you also, of course, need a PS to Simulink in order to send the signal, this position, to scope. And in order to send these Simulink blocks to these physical systems, you need this block, which is basically called Simulink to physical system converter. So you of course need to connect one of these solver configurations here, and here we are going to run it for 10 seconds, and we are going to see the results. I will give you a download link for this file if you want to play with it and learn from that. So this is the same problem that I talked about, and these are the solutions. Look, this is X1 and this is X2. Now you see initially there is a little bit transition. They start from some initial conditions, they drop, and then they go stable. So you see after about 3-4 seconds, their behavior is not changing. The only thing is, if you look at these behaviors, there is not a single frequency in them, okay? If you look at this green signal, you see there are 2 peaks, and that is because there are 2 harmonics inside the signal. So when you get 2 harmonics, you're not going to get those beautiful signs. You're going to get several peaks inside your wave. So this is the response of the system, but this solution is numerical solution, of course. This is done in Simulink with a variable ODE solver, but if you want, as I said, as long as you can solve for those 8 unknowns somehow with a numerical solver like Newton-Raphson, you should be able to get full analytic solution in this system as well. So hopefully this video was useful to you, and I'll see you in the next lecture. Thank you.